Hello friends, welcome to your channel that is Civil Engineering Choice, and we have started the series to calculate the shear force and bend moment diagram, and these are the contents that we are trying to cover in the unit 2 that we are considering as a shear force and bend moment diagram. Okay, and when we are calculating the shear forces and bend moment diagram of the simply supported beam carrying a different types of loading, so in that case we can see these are the types of loading that comes in the numerical. So we have to calculate the shear force and bend moment of that particular loading. Okay, the first load, point load will be there, and that point load will be vertical. Vertical means, let's say this is our beam and the vertical point load is acting on that beam. Okay, second type of loading is incline loading. Point load per incline loading means, suppose if any beam is there and the maybe load will act as an incline, so we have to calculate the shear force and bending moment of such type of loading also. Then next one is the UDL. UDL means uniformly distributed load. Okay, so already we know that what is meant by uniformly distributed load. Suppose beam is there and the load is uh, distributed over the span of beam is uniformly, that load is called as a uniformly distributed load. Okay, and next one is UVL. UVL means uniformly varying load. Okay, uniformly varying load means what? Suppose we have A and B point on the span of beam, and whatever loading is acting on that beam, the intensity of that loading is not same from A point to B point. Okay, it may be vice versa, means maybe intensity at B point is maximum and at A point is minimum. Okay, or maybe it like this. Okay, so any kind of loading that intensity is not constant from A point to B point, the such type of loading is called as uniformly varying load. Okay, so we have to calculate the shear force and bending moment of that particular load case also. So we are going to cover the numerical on this type of loading. Okay, so all types of loading that we are going to cover, or we will cover the numericals on all types of loading. So next one is the couple. Okay, couple or moment. Let's say suppose we have the one beam, and that beam having the couple or the moment at a particular point, whether that moment is clockwise or anti-clockwise. So such case is also there. So we have to calculate the shear force and bending moment for this case. So I think already we have covered one numerical on this type, but we will take the combination of all the loads or some loads, like one point load is there and one couple is there, one point load, one UDL is there. So some variation of loading of numericals that we are planning to upload to understand the actual basic or actual concept of shear force and bending moment diagram. Okay, so how many types of numericals may be that can be asked in the exam, or that we need to calculate for the shear force and bending moment diagram? So first one is the numerical on the simply supported beam. Numerical on simply supported beam means, maybe one simple support beam is there, and that simple supported beam is subjected to a point load, whether it is vertical or inclined, or UDL or UVL or couple. Okay, so that case may be there, so we need to calculate the shear force. So this is the first type of numerical that we have to solve, or we have to calculate the shear force and bending moment diagram. The second type of numerical is also there, that is uh, numerical on overhanging beam. Overhanging beam means what? The beam is continuous after the simple support. Okay, let's say this is our simply supported beam. Okay, and the span is continue, or we can say the cantilever span is continue beyond this support. Okay, let's say this is A support and this is B support. When the point the span is continue beyond the B support, so that particular portion is called as a overhanging portion, and the total beam is called as a overhanging beam. Okay, so such type of numerical also we are planning to upload for the shear force and bending moment diagram. The next one is the cantilever beam. Okay, numerical on the cantilever beam. We know the concept of cantilever beam. One end is fixed and another end is free. Okay, so these types of numerical that we are planning to cover to calculate the shear force and bending moment diagram. And today we are going to discuss only simple numerical, that is simply supported beam, and simply supported beam carrying a 3-point load, that is 5 kilonewton, 10 kilonewton and 8 kilonewton, and that will act at 2 meter from A point, then 2 meter from C point, 3 meter from D point. Okay, so distances are there, and we need to calculate the shear force and bending moment diagram. So first we will see how that shear force and bending moment diagram uh, is there for this particular load C. Okay, so this is the shear force and bending moment diagram that now we are uh, calculating. Now we are calculating actual forces at the each point, that we will see, but here we can see just the diagram how it is behave under this 3-point load. Okay, so this is the shear force and bending moment diagram. Okay, so let's start with the numerical. Okay, so as we discuss here, we are considering one simply supported beam, and that simply supported beam having 3-point load, 5 kilonewton, 10 kilonewton and 8 kilonewton. So 5 kilonewton load is act at 2 meter from the A point, then 2 kilonewton, 10 kilonewton load is act at 2 meter from the C point. Okay, means if we consider the distance from A point, it is 4 meter. Okay, then another 8 kilonewton force is act at 3 meter from the D point, means the total distance is 2 plus 2 plus 3, that is 7 meter. Okay, 7 meter. So this distance we are considering, and if we see the total span is 8 meter. Okay, this is our total span. So this is a simple problem statement that we are considering to calculate the shear force and bending moment. Okay, and then draw the shear force and bending moment diagram. So as we know that to calculate the shear forces, to draw the shear force and bending moment diagram, first we have to calculate the support reaction, then we have to focus on the shear force calculations at each point, and then third step is calculate bending moment at each point. Okay, so already we have discussed how to calculate the shear forces, how to calculate the bending moment, everything we have discussed already. Suppose you have some doubt, so you can refer my previous video to understand how to calculate the shear force and bending moment diagram. Okay, so as we know that for the calculation of shear force and bending moment diagram, first we need to calculate the support reaction, and for support reaction we can use any sign convention. Generally we are using three equilibrium condition, that is summation, basically we have three equilibrium condition, that is summation fx is equals to 0, summation fy equals to 0, and then summation m is equals to 0. Okay, these three equilibrium conditions are there, but we are using only two equilibrium condition, that is summation fy equals to 0 and summation m equals to 0, because there is no any horizontal force, only vertical forces are there. That's why we are using these two equilibrium conditions, and out of that we are using first equilibrium condition, that is summation m is equals to 0, and we are taking moment at a point, that's why we can call it summation ma is equals to 0. Okay, so apply first equilibrium condition, that is summation ma equals to 0, and when we apply summation ma equals to 0, so what will be the equation? That is first, now see, for the equilibrium condition we can use any sign convention, and now here we are using clockwise moment as a positive. So if you see the let's say this is our reaction at a point, that is ra, and the reaction at b point is rb. Okay, these are the support reaction. So first apply 5 into perpendicular distance. First force is what? 5 into perpendicular distance, that is 2. Okay, 5 into 2, here we can see 5 into 2. We have not taken moment of that ra because we are taking moment at a point, and if we consider ra into perpendicular distance, so perpendicular distance from a point of that ra support reaction is 0, that's why we are not taking taking this moment. Okay, then after that take the moment of 10 kilonewton, and force 10 having distance from a point is 4 meter. Why we are taking the distance from a? Because we are taking moment at a point, so 10 into 4, and similarly here we can see 8 into, means this force 8 kilonewton force into perpendicular distance is 7 meter. Okay, so likewise you can calculate the moment. Now last force is there, that is rb, and if you see the moment of 5, moment of 10 kilonewton, and the moment of 8 kilonewton is a positive, that's why we have taken it as a it is clockwise, that's why we have taken it as a positive. But moment of rb, okay, moment of rb is anti-clockwise, so we need to take it minus as per our sign convention, and the distance is 8 meter. Okay, so we have taken the moment. Okay, now we have to solve this equation. Once we solve this equation, we will get the final force or the support reaction at b point, that is rb, and that rb is equals to 13.25 kilonewton. Okay, so rb is 13.25 kilonewton, means the support reaction at b point that we have calculated. Okay, the first equilibrium conditions that we have applied. Now apply another equilibrium condition, that is summation fy is equals to 0, and let's see what is the summation fy equals to 0, means sum of all vertical forces. And if you see, there are few forces, vertical forces, that is ra support reaction, it is vertical force, rb support reaction, this is also vertical force, and 5 kilonewton, 10 kilonewton, and 8 kilonewton, these forces are the vertical forces. Okay, but before that we need to decide the sign convention, and generally for support reaction we are considering upward force positive and the downward force negative. Okay, these sign conventions we are considering. So here we can see ra is positive because of upward, rb is also positive because of upward, but whatever these three forces are there, these three forces are negative. Okay, so the equation will come ra plus rb, okay, minus 5 minus 10 minus 8 is equals to 0. So here we can see that equation. Okay, see, ra plus rb minus 10 minus 5 minus 10 minus 8 is equals to 0. Okay, but already we know rb we have calculated, that is 13.25. Just put the value of rb and then solve this equation, we will get ra is equals to 9.75. Okay, It means we have calculated the shear support reaction at A point and support reaction at B point. Here simply we can see at A it is 9.75 and at B it is 13.25 kilo Newton. Okay, why kilonewton? Because our total force are in a kilonewton. Okay, now first step that we have completed to calculate the support reaction. Now next step to calculate the shear forces. Okay, and first thing we should remember while calculating the shear forces at each point, that is sign convention. Okay, so already we have discussed how to decide that sign convention. So as per that sign convention, if you take the section between that these 2 points, so if the force is upward in left of the section, that force we need to consider as a positive. Okay, and generally for the simply supported beam, we are starting our calculation from left to right. Okay, always if simply supported beam is there, so always start your calculation from left to right for the shear force as well as for the bending moment. Okay, now again we know that for the calculation of shear forces we need to take point one by one point, and then take a section on left of that particular point and section on right of that particular point. It means we have to calculate the shear force at A left and shear force at A right. Same for C, D, E and B point. Okay, so these shear forces we have to calculate at the left and right part of that particular section. So we will take one by one. So let's say shear force A left. Okay, shear force A left means what? We are considering shear force or the section on left of that A point, and if we focus on the left, why we are focusing on the left? Because we have started our calculation from left to right. Okay, so if you focus on the left of that particular section, there will be no any force. That's why shear force A left is equals to 0. But if you take the shear force at A right, okay, so if we take the shear force at A right, so there will be one force, that is RA, and RA is upward. So as per our sign convention, okay, as per our sign conventions, we have to take RA as a positive, and RA already we have calculated, that is 9.75. Okay, so the shear force A right is 9.75. Okay, so shear force that we have calculated. Now after that, take a section. Okay, here we can see that variation of shear force. See, the shear force is going upward from for the right side. Okay, now again take the section on left of C point. Okay, section on left of C point, and then focus on left, only RA. Again only RA is there. It means shear force C left is also, okay, shear force C left is also RA, that is 9.75. It means our shear force diagram is constant from A right to C left. Okay, A right to C left, A right to C left. Okay, now after that, take a section on right of that point, C point, and then focus on left. And if you see on the left of that particular section, there are two forces, that is RA and 5 kilonewton. Okay, so RA is upward, that is 9.75, and this 5 kilonewton is downward, that is minus. So the shear force on shear force C right is what? 4.75 kilonewton. Okay, and it is also positive. So here we can see it. Okay, shear force C right, RA, okay, RA minus 5, that is 9 point, RA is 9.75 minus 5, that is 4.75, and it is positive. Okay, so whatever shear force diagram is there, that shear force diagram will goes down at the 4.75, because value at C left, okay, value at C left should be 9.75, that we can see, and the value at C right is 4.75. That's why shear force diagram will suddenly drop. Okay, now next point is there again, that is D. So we have to take the shear force at section at D left. Okay, D left, and then focus on left of that particular section. And if you see on the left of that section, again there are two forces, that is RA and 5 kilonewton. Okay, RA is upward. Okay, so D left, RA is upward and 5 kilonewton is downward. So 9.75 minus 5 is equals to 4.75, means up to D left, whatever shear force diagram you have considered here, that shear force diagram is constant. Okay, now then after take a moment, then after take the section at D right. Okay, and then focus on left. Now if you see here, there are three forces, that is RA, 5 kilonewton and 10 kilonewton. Okay, so for section B right, we need to take all these three forces. RA is upward, that's why I take positive. 5 kilonewton and 10 kilonewton downward, that's why I take it negative. So see here reaction, D right, shear force D right, RA positive, minus 5 minus 10. So RA already we have calculated, that is 9.75. So 9.75 minus 5 minus 10. So the answer will be minus 5.25. Okay, the answer is minus 5.25. It means that shear force diagram which goes down means this is a baseline. Okay, if value is minus, it means we have to consider that value below to the baseline. Okay, it means that the shear force diagram will suddenly drop and it comes to the down. Okay, see likewise. Okay, so up to the D right we have calculated. Then after calculate the shear force at E left. Okay, again calculate or again take the section on E left and then focus on left of that particular section. Again three forces are there, that is 9 kilonewton, 9.75, 5, 10. Okay, means whatever equations we have calculated for the D right, that equation is same for the E left. So shear force E left, it is same, RA minus RA, then minus 5 minus 10, that is minus 5.25. So it means that shear force diagram is constant up to the E left. See here. Okay, shear force diagram is constant up to the C left. Okay, now again take section on E right, then focus on left. Now four forces are there, that is 9.75, 5, 10 and 8. Okay, where 5, 10 and 8 are downward, so we need to take it as negative as per our sign convention, and RA is upward, so it should be positive. Okay, so the equation on E right, see equation on E right will be RA positive, then minus 5 minus 10 minus 8. Okay, so it will be minus 13.25. Means at E right the shear force diagram is again suddenly drop. Why drop? Because of this value is minus 13 and previous value is minus 5, so again it is suddenly drop, so it is minus 13.25. Okay, so when we are considering that value below the baseline, so no need to consider the sign. Okay, means no need to draw sign or no need to show the sign, means minus 5.25 minus 13.25 likewise. Okay, once you show that value below the baseline, it means by default that value is minus. Okay, now B left. Okay, after that B left, again if you see, if you take the section on B left, again four forces are there. It means whatever equations we have considered over here, that equation is applicable to B left also. Okay, so it is same, minus 13.25. It means that shear force diagram is constant from E right to B left like this. Okay, then lastly B right. Okay, if you take the section on B right and then focus on left, again now all these three forces are coming and these two support reactions are also comes in picture. Okay, so RA upward, RB upward, so RA and upward will be upward, therefore that will be positive, and 5, 10 and 8 is downward, so it should be negative. Okay, so RA positive, minus 5 minus 10 minus 8 plus 13.25. Instead of RB directly I have put a value of RB, that is 13.25, and once you solve this equation, so it is 0. Okay, it means whatever shear force is comes on B left, it should be comes at the 0 point for the B right. So this is shear force and bending moment diagram, and if you see over here, when the shear force is above baseline, so we should consider this shear force diagram as a positive and this shear force diagram as a negative. The simple way that in simple way we can calculate the shear forces of each point. So once you calculate the shear force, the next thing is what? Calculate the bending moment, and we know that to calculate the bending moment we are considering, okay, we are considering the points. Okay, means we have to calculate the bending moment at A point. Okay, as this bending moment at A point, bending moment at C, then D, E and B. So each point we have to calculate the bending moment. Okay, no need to consider left and right. Okay, but before that, again the most important thing is what? Sign conventions, and we are going to consider the sign conventions. How we are considering the sign conventions, already we have explained it. Just go my previous video, you can find the link of that previous video in my description box. So just go through that and see how I have considered that sign convention. Okay, so as per that sign convention, if any movement is on left of that particular section, so it is clockwise. Now clockwise movement should consider positive. Okay, clockwise movement should be positive, and just focus on left, because for the simply supported beam we are always starting our calculation from the left to right. For shear force calculation, for bending moment calculation, for every calculation, for every simply supported beam, always start your calculation from left to right. So without wasting time, just calculate the shear force bending moment at the each point. Okay, bending moment at the each point, so bending moment at A point. Okay, 0, because we are taking section at A point and then focusing on left, there is no any force, so no any movement. Okay, after that take the section at C point and then focus on left, so there is one force, that is RA. So RA into perpendicular distance, so movement is clockwise, clockwise, so it should be positive. So ra into perpendicular distance is how much? Perpendicular distance is 2. Okay, so we'll see moment at C point. The moment at C point, ra into 2, that is 9.75 into 2, that is 19.5 kilonewton meter, and it is positive. So the bending moment diagram goes positive up to the C point. Okay, then after take a moment at D point. Okay, again by taking moment at D point, so there are two forces. Okay, there are two forces on left of that D point, that is ra means 9.75 and 5. So the moment will be ra into perpendicular distance, how much? 4 from D point. Okay, 2 plus 2 from D point, it is 4, and due to the clockwise movement it is positive. Okay, then movement of this 5, it is anti-clockwise, so minus 5 into perpendicular distance from D point, it is 2. So the equation is 9.75 into 4 minus 5 into 2. So let's solve this equation. So we will get the moment at D point. See, moment at D, ra into 4 minus 5 into 2. Okay, so it will be 29 kilonewton meters. 29. Then again take movement at E point. So on left of E point, three forces are there. So ra into perpendicular distance 7. Okay, here we can see ra into perpendicular distance 7. No, ra is what? 9.75. So I have put that value. Then movement of this 5 into perpendicular distance, how much? From the E point, it is 2 plus 3, that is 5. Okay, this 5. Then movement of this 10 into perpendicular distance 3, so 10 into 3, that is 13.25. So it is goes down up to the 13.25 at E point. See, like this. And last point moment at B point, again take a section at B point and then focus on left. Okay, then focus on left. So three forces and one support traction is there, correct? So the equation will be first ra into perpendicular distance, how much? 2 plus 2 plus 3 plus 1, that is 8. So 9.75 into 8, then 5 into perpendicular distance, 2 plus 3 plus 1, 6, correct? 10 into perpendicular distance, that is 3 plus 1, 4, and 8 into perpendicular distance 1. Just solve this equation, we will get a value as a 0. Okay, so it means this bending moment diagram goes at the 0 at B point. So this is close. Okay, and see, total bending moments are positive, and we have drawn this bending moment above the baseline. It means this bending moment diagram we can say as a positive. And see, this is a bending moment diagram theoretically, but practically means on field, some structural engineers are showing this bending moment diagram below the baseline. Okay, below the baseline like this. Okay, so you can show that bending moment diagram like this also. It is depend. Okay, but theoretically it is correct. So this is a simple problem statement today that we have covered. Simply supported beam carrying 3-point load, and again see jhalak of shear force and bending moment diagram under this 3-point load. See, just in fast mode. Then right, then again down, then again right, and then it will close, stop. Okay. Okay, so thank you so much for watching my video. And see, as we are discussing in every video, I am planning to upload all the topics which are related to structural subjects, that is engineering mechanics, strength of material. We have started the strength of material, structural analysis, design of reinforced concrete structure, design of steel structure, design of pre-stressed concrete structure. Okay, and some miscellaneous parts also we are trying to cover. And the most important, so most important points, those are required as a field point of view, that point also we are covering. Okay, so please like and subscribe my channel so you will get the notification. Okay, thank you so much.